Okay. One more piece of notation. I will use script P gamma to denote the set So script P gamma will denote the set of Pareto efficient strategy profiles. Again, when we talk about Pareto efficiency, we talk about strategy profiles, not strategies. Okay? You have to be careful about that. So let's look at the prisoner's dilemma game. What is the set of Pareto efficient strategy profiles in the game, in the prisoner's dilemma game? So first, is CC Pareto efficient? No, right? So if you say it's not Pareto efficient, it means that something Pareto dominates it. What Pareto dominates it? DD, right? Since U1 of CC is bigger than U1 of, U1 of DD is bigger than U1 of CC, and U2 of DD is bigger than U2 of CC. DD, Pareto, dominates CC. Hence, CC is not Pareto efficient. CC is not Pareto efficient. What about CD? Is CD Pareto efficient? No. Then, if you say it's not Pareto efficient, you have to tell me a strategy. You have to give me a strategy profile which Pareto dominates. What Pareto dominates? CD. Sorry? DD? Yes? Sorry? Worse off. What does that say about Pareto domination? Sorry? But look at the definition. They don't. You see? This statement is either true or false, which means that S prime either Pareto dominates S or does not. There's nothing in between. Okay? If this statement is true, S prime Pareto dominates. So if I put CD for S, and I don't know, DD for S prime, if this statement is true, then it means that DD Pareto dominates CD. If this statement is false, then it means that it doesn't Pareto dominate it. Okay. And actually, because of the reason that you said, you see one of them is better, but the other one is worse, it means that DD does not Pareto dominate CD, you see? So when we compare DD to CC, for player 1, CD is worse than DD. Just because of that, DD cannot Pareto dominate CD. So again, the whole thing is, you see, when we moved from here to here, when we compared CC to DD, okay, agent 1 became better off, agent 2 became better off. Because of this, nobody is hurt. This says when you go from the outcome induced by S to the outcome induced by S prime, nobody becomes worse off. At least one individual becomes better off. Well, when we move from the outcome induced by CC to the outcome induced by DD, nobody becomes worse off. At least one person, actually in this case, both of them become better off. That's why DD Pareto dominates CD. Now let's look. If we move from CD to DD, agent 1 becomes worse off. Because of that, DD cannot Pareto dominate CD. Okay? So far, so good? So since U1 of CD is bigger than U1 of DD, DD can't Pareto dominate CD. Because for Pareto domination, we need this condition. Okay? So, well, DD does not Pareto dominate it. Maybe DC does. Does it? No. Why? When we move from here to here, agent 1 becomes worse off. So again, just because of that, even though agent 2 becomes better off, agent 1 becomes worse off. Because of that, DC cannot Pareto dominate CD. Well, maybe CC does. Does it? When we move from here to here, player 2 becomes better off. But again, player 1 becomes worse off. So CC cannot Pareto dominate CD. Well, then what happened? It's Pareto efficient. Nothing Pareto dominates CD, so it is Pareto efficient. What about DC? The same reasoning. So DC is also Pareto efficient. What about DD? It's also, so you check. Can CC Pareto dominate DD? No, both agents are worse off. Can CD Pareto dominate DD? No, when I move from here to here, player 2 becomes worse off. Can DC Pareto dominate DD? No, when I move from here to here, player 1 is worse off. So DD is Pareto efficient. So the set of Pareto efficient strategy profiles in the prisoner's dilemma game is CD, DC, DD. That is, all strategy profiles except CC, which was the strictly dominant strategy solution of this game, which was what we would predict for any rational group of players to play. For any rational, selfish players to play. That's where the dilemma is. Adam Smith said if individuals work for their own benefits, the result would be the best for the society. Well, that's not the case. Individuals behaved selfishly, did what is best for themselves. We ended up at a socially bad situation. Socially bad in what sense? In a sense that there is an outcome which both prefer to the outcome induced by CC. Okay? That's where the dilemma part is. Okay? So far, so good? Any questions? Any questions? Then what is the next question you should ask? Again, the attendance sheet, please sign, passed around. So we have a new animal. So far, what are the animals we have? Strict dominant strategy solution concept, dominant strategy solution concept, Pareto efficient strategy profiles. Well, we can think of this as also a solution concept because it takes games and maps it to subsets of strategy profiles. So we can say Pareto solution concept, Pareto efficient strategy solution concept. Okay? So once you have a new object, the first question you should ask is, does it always exist? You make a habit of this, right? In the future, when you do some research, these are questions that should be answered immediately. Okay? So, does every game have a Pareto efficient strategy profile? Does it always exist? What is your guess? You don't know the reason. Anybody else? So your friends guesses, and that's good. You have to make guesses. And then you try to prove it. Okay, you use your gut feeling to make an initial guess. It might be wrong, but we also learn from our mistakes. We also learn from our wrong guesses. So, anybody else? Yes, sir. Pareto dominant strategy? Okay, but be careful. So your friends say, let's say that we have a Pareto dominant strategy. Well, Pareto domination is about profiles. So saying that, let C be a Pareto efficient strategy is not a meaningful sentence because strategies alone cannot be Pareto efficient. It's always about, but I'm glad that you see, we learn from mistakes. If we haven't taught that, some of you might have made this mistake. Strategy, when we talk about Pareto efficiency, it's always about strategy profiles. Okay?
What is again the exact difference between strategy profiles and
strategy profile is a list of strategies. So CC is a strategy profile. C is a strategy. C alone does not determine an outcome. So I can't say I prefer C to D. I have preference over outcomes. You see, the notation we used was, we wrote CC, I don't know, what did we say? Well, we wrote DD preferred by player 1 to CC. What did this actually mean? The outcome induced by DD is preferred by player 1 to the outcome induced by CC. Okay? But C alone does not induce an outcome. So saying C is preferred to D or vice versa is not meaningful. Okay? So because of the way we write it here, it's about strategy profiles. Okay? So do you want to take it? Which is Pareto efficient. So what do you mean by Pareto dominant? Pareto dominates every other. Okay, so, okay, by the way, again, Pareto efficiency does not mean that Pareto dominates every other strategy profile. But if that is the case, of course, it is Pareto efficient. Okay, so, so wait a minute, come again. So what do you start with? Take a strategy profile. What do you want about that? So first of all, your friend's claim is non-empty for any game gamma. So what is the idea behind this? How do you think that that's the case? Repeat that again. Okay, so let me say that. So your friend starts by saying let S prime Pareto dominate any other strategy profile. Yes. Okay. So just because of that, if S Pareto dominates every other S, does that imply that S prime is Pareto efficient? Yes? How do you know? It's not Pareto. It cannot be Pareto by any other strategy by using the definition. Which reminds me, you see, strict domination, Pareto domination, those induce a binary relation over, well, for strict domination and domination over strategies, for Pareto domination over strategy profiles. So you see, we say that S prime is related via Pareto domination to S if and only if this condition holds. Okay? So this definition induces a binary relation over the set of strategy profiles. Whenever you have a binary relation like this, there are certain questions that are good practice to ask. Okay? What kind of properties does this binary relation satisfy? So what kind of relations do we have what kind of properties do we have on binary relations? Completeness. So ask yourself, is the Pareto domination relation complete? Is it? That is, take any pair of strategy profiles. Can we always compare them? That is it the case that S Pareto dominates S prime or S prime Pareto dominates S? they can be incomparable, right? That's, so for example, again, let me write the prisoner's dilemma. I'll just write simple numbers here. Well, I'll just, what do we have? I forgot. Okay, so CD does not Pareto dominate DC, nor DC Pareto dominate CD. Okay, so it's not, Pareto domination is not a complete binary relation over strategy profiles. There would be a pair, there could be some pair of strategy profiles which are incomparable via the Pareto domination relation. So it's not complete. What other properties can a binary relation have? Transitivity. Is Pareto domination relation transitive? Yes, no, maybe? If so, what the question is, if S Pareto dominates S prime, and S prime Pareto dominates S double prime, does that also imply that S Pareto dominates S double prime? Yes, well, you can, I'm not going to prove it, you can easily check it. So Pareto domination relation is transitive. What else can we ask? Well, let me ask, these are the standard relations that we use in economics. One thing we can ask is it asymmetric? That is, so let me write that, a relation. I don't know, PI is asymmetric if and only if for any S prime in S PI S prime implies that it is not the case that S prime PI S. So if this condition holds, we say that this binary relation is asymmetric. So the Pareto domination relation is asymmetric if whenever S Pareto dominates S prime, then we can conclude that S prime does not Pareto dominate S. Is that the case? Again, because of that condition, the answer would be yes. If I'm not going to do it, it's just simple algebra. If S prime Pareto dominates S, S cannot Pareto dominate S prime. The Pareto domination relation is asymmetric. Ask the same questions to yourself for dominance relation, strict dominance relation. Okay? So because the Pareto domination relation is asymmetric, it means that if S prime Pareto dominates any other strategy S, then no strategy can Pareto dominate S prime. So which means that S prime is Pareto efficient by the asymmetry property of the Pareto domination relation. Okay, so what? I'm sorry I intervened with your. So in that case, S prime is Pareto efficient, so this set is not empty. Okay. What if there is no such strategy? This is a very exceptional case. So then the negation of this is that there is no strategy which Pareto dominates every other strategy. So how can you use that? What is the conclusion from that? Well, but those are for two pairs. Actually, let's.
You take every two possible pairs in the chain.
So maybe in.
Follow us the chain, like if we compare the first two strategy profiles, and then
Compare the first two strategy profiles. Okay.
go on as a chain. And if we have
Okay.
strategy that dominates any other S, it's the result that.
Uh-huh.
If it doesn't, then we will compare like the strategy profile with any other strategy profile, any other of these in our set.
Okay.
So with each of them, it either will be Pareto dominated, or it will either Pareto dominate them or not.
So let's try to refine your idea a little bit, because you did two things. First, you said, let's take pairs, and then you took one strategy. So let's start. Let's take the strategy profile. So simple illustration, not a proof, just to get an idea. Let's take the strategy profile. The strategy profile which corresponds to this cell. So, okay, if this is Pareto efficient, we're done. It's not empty. So let's try to find an example where this set is empty. For that set to be empty, what should we have? There should be a strategy profile which Pareto dominates this. So let's say that it's this one. So let's say that this strategy Pareto dominates this. So if this is Pareto efficient, we're done. It's not empty. But we want to force it to be empty. So let's say that this is not Pareto efficient. Then what should be the case? There should be a strategy profile which Pareto dominates this. Can it be this? No, why not? Because of asymmetry. It can't be this because of asymmetry. So it should be one of these other cells. So let's say that it's this. Okay. So this strategy profile, Pareto dominates this strategy profile, which implies that it also Pareto dominates this one. Why? Because Pareto domination is transitive. So again, we're trying to find an example where this set is empty. So then this, if this is not Pareto efficient, it means that there's something which Pareto dominates it. Can it be this or this? No, because of symmetry, it can't be this. So it should be some other cell. So let's say that it's this. By transitivity, so this strategy profile Pareto dominates this. By transitivity of the Pareto domination relation, this strategy profile also Pareto dominates this, and also Pareto dominates this. By asymmetry, this profile cannot Pareto dominate this profile. This profile cannot Pareto dominate this profile. This profile cannot Pareto dominate this profile. So it's this profile is not Pareto efficient. There should be some strategy profile which Pareto dominates this. And it can't be one of these. And I will keep going on like that. And then I will come up to this cell. Okay, what happens? Well, this profile cannot Pareto dominate this because of transitivity. This can't, this can't, this can't, this can't, this can't. So what happened? This profile at the end, we will have to end up with a Pareto efficient strategy profile. What did we use? We used asymmetry and transitivity of the Pareto domination relation. Okay? Yes, sir. So we started with, so your friend's question is, I started with the strategy profile. Okay? So as you said, there's two options. This is either Pareto efficient, which means that the set is non-empty, right? Or it is not Pareto efficient. What does not Pareto efficient mean?
There's something else that dominates.
There's another strategy profile which Pareto dominates it. So how did we choose this? We said, if this is not Pareto efficient, there has to be something else, as your friend said, some other strategy profile which Pareto dominates it. That's where we came to this. Okay? So far, so good? So far, so good? Yes, sir. Okay, yeah. In this case, yes. So the thing is, what happened? I tried to find a situation where there is no Pareto efficient strategy profile. And what did that force me to do? Well, it forced me to a game which a strategy profile Pareto dominates every other strategy profile.
So it's at least one.
There's at least one. Okay? Of course, from the prisoner's dilemma again, we know that there could be three. There could be many. Okay? Any questions? Yes, sir. Sorry, what if there is?
Then all of them are Pareto.
Well, wait a minute. If there is no Pareto dominant strategy profile, what if? But you see, that's what we started with. It said, let's assume that this game does not have any Pareto efficient strategy profile. So I said, close my eye, choose the strategy profile, anyone. Let's say This one. Well, because there is no Pareto efficient strategy profile, this cannot be Pareto efficient. If it's not Pareto efficient, something else must Pareto dominate it. Let's say that it's this strategy. Okay? Well, and then I said, well, is this strategy Pareto efficient? It can't be because we said there is none. So this must be Pareto dominated. Well, what can Pareto dominate? It can't be this because Pareto domination is symmetric. It should be something else.
I think he's asking if all of them are equal.
If,
For example, if we say that at CC we have -2, 4.
at CC we have -2, 4. In this case, what is the set of Pareto efficient strategy profiles? Everything is Pareto efficient. Okay? Was that? Okay, sorry, I misunderstood. Thank you, thank you. Okay? So everything is Pareto efficient, it's not empty. Okay? So far, so good? What if they're, okay, what if they're all equal? Just a simple example, 1, 1, 1, 1. What is the set of Pareto efficient strategy profiles for this game? Everything, okay? Again, that's for Pareto domination. So for example, let's call this top, bottom, left, right. So for example, for TL to Pareto dominate, I don't know, BR, what should happen? When we move from the outcome induced by TL to the outcome induced by BR, nobody should become worse off. Nobody becomes worse off. At least somebody should become better off. Is there anybody who's becoming better off? No, which means that BR does not Pareto dominate TL. Well, what was the condition for Pareto efficiency? Again, the warning I gave you at the beginning. Pareto efficiency doesn't mean that it Pareto dominates everything else. It means that it is not Pareto dominated. So TL is not Pareto dominated because when we move from TL to TR or BR or BL, there's nobody who's becoming better off. For domination. Okay? Yes, ma'am. Okay, what if the strategy set is infinite? That's what I was expecting. You see, what did we do here? We went step by step and we said, hey, well, there's the last cell. Well, there will be a last cell only if the strategy sets are finite. So your friend is right. If the strategy set is infinite, this argument will not work. Maybe it will go on forever. Then we have a problem. You're right. So actually, this is not a proof, but I recommend that you try to write a proof. What we have is the following proposition. For any finite game gamma. What do I mean by finite? First of all, we always assume that the set of players is finite. There's no problem with that. So when I say finite, what we mean is the strategy set of each player is a finite set. So for any finite game gamma, this set of Pareto efficient strategy profiles is non-empty. So every finite game, if I want to say it in plain English, every finite game has at least one Pareto efficient strategy profile. Every finite game has at least one Pareto efficient strategy profile. Okay? So far, so good? So far, so good? What if the game is infinite? That is, what if at least one of the players has a strategy set which is not finite? Then this argument will not work. Right? So I'll leave it to you as an exercise to either prove it or give a counterexample for this proposition when the game is not finite. I'll leave it as an exercise to you. Okay? Any questions? Any questions? But I'll just add one more proposition about. So at least, this is good news, at least for finite games, we know that there is Pareto efficient strategy profiles. Okay? Okay? So let gamma gain, well, let me write it like this. Where for each agent, I'll change markers. For each agent, UI is a numerical, representation of the preference relation Ri. Okay? So rather than working with preferences, let's take numeric representations. Now we'll see one of the powers of numeric representations. Okay? If a profile S star in S is satisfies the following. Summation UI S star I in N is greater or equal to summation UI of Si in N, for which S? For any strategy profile S. Then what holds? What happens? So S star is a profile which maximizes the sum of the numeric representations of the preferences. It maximizes the sum of the numeric representations, so I'll use the short way, utility functions, over the set of strategy profiles. What does that say about S star? It's Pareto efficient. So usually finding Pareto efficient strategy profiles is a bit painful, okay? But this tells you at least one way to find them. Take numeric representations, maximize the sum. The result would be Pareto efficient. But again, be careful, this is an if-then statement. So if it maximizes, it's Pareto efficient. Whenever you have a statement of the form P implies Q, you should immediately ask, does it work the other way around? Is it an if and only if statement? Is it the case? No, right? Again, you can easily write an example. Let me write a 2x2 example. I don't know. Yep. What am I doing? Well, it doesn't really matter. I'll just, no, I don't want this. I'm sorry. Let me try to write the, okay. So here, everything except top, bottom, left, right. Top left is Pareto efficient, but the sum is maximized at BL and TR. So because the sum is maximized, so 5 plus 1, 6, 1 plus 5, 6, 2 plus 2, 4. So because TL at TL and BL, at TR and BL, the sum is maximized, we conclude that both of them are Pareto efficient. The sum at BR is 4. It's not maximized, but BR is also Pareto efficient. Okay? Okay? So far, so good? Any questions? Any questions? Okay. Well, so let's talk a little bit more about this. Let's talk. So if it's finite, there's Pareto efficient strategy profile. If a strategy profile maximizes the sum of the numeric representations, it's Pareto efficient. So there's a So if this maximization problem has a solution, then there's a Pareto efficient strategy profile. So the next question you can ask is, under what conditions is there a strategy profile that maximizes the sum of the numeric representations? What is the condition that will guarantee for the existence of a maximizer? Exactly. So one is compactness, but that's not enough alone. Continuity. So if you remember from Math Econ, and I think engineers should have read about that in Calculus 2, or Calculus 1, I don't know, somewhere. If we have a theorem, Weierstrass maximum theorem, let me write that. So I'll write the simple form. Let X be a subset of some Euclidean space. It would be a compact, change the marker, compact set, and F, a real valued function on X, which is continuous. Function. Okay, so if X is compact and F a continuous function on X, then Weierstrass tells us that F has a maximizer over X. Then there exists an X star in X such that F of X star is greater or equal to F of X for every X in X. Okay, so if your domain is compact, that is closed and bounded, okay, and your function is continuous, we are guaranteed for the existence of a maximizer. So if your strategy profiles is a subset of the Euclidean, if your set of strategy profiles is a subset of the Euclidean space which is compact, okay, and your numeric representations are continuous, we are guaranteed for the existence of a maximizer, which means that we are guaranteed for the existence of a Pareto efficient strategy profile. Okay, we'll come to this. We'll do an example with that. But I said if this is not true, you have to find an example. The example that you should find is either an example where the set of strategy profiles is not compact, or it doesn't have preferences, does not have a continuous numerical representation. Okay? Think about it. Next lecture, we'll talk about that. Any questions? What is a compact set? Well, this is something that we're going to be using, so I'd like to spend some time on it. So first of all, compactness is a topological concept. I'm not going to give you the most general definition. So those from the math department usually see a different definition for compactness. We're going to be working with Euclidean spaces, that is spaces of the following form, are K, where K is a natural number, okay? So when we're talking about the Euclidean metric spaces, Euclidean spaces, compactness is equivalent to the following. If and only if X is closed and bounded. Okay. So what does closed and bounded mean? Again, I'll give you not the, so by the way, those who study real analysis or topology, compactness would mean that every open cover should have a finite subcover, whatever that means. But you don't have to worry about that in this course. For us, that's what it means, okay? So what does closed mean? Again, the general definition is a bit different. Closed means complement of it should be open, but I'll give you a different notion. for us, closed means the set contains every boundary point. Okay? So what is a boundary point? So take, for example, this set. Okay? The boundary points of this set is, what do you think it is? 0 and 1. So the boundary points of this set is 0, 1. 0 is not an element of this set, hence this set is not closed. Okay, because it doesn't contain a boundary point. What is the set of boundary points of this set? What is the set of boundary points?
0.
Again, 0 is a boundary point, 1 is a boundary point. There's 2 boundary points, 0 and 1. They're both included in the set. So this is a closed set. Okay? Boundary points of this set? Only 0. 0 is in this set. So this set is a closed set. Okay? So closedness means contains all the boundary points. Again, for our purpose. Closedness means contains all boundary points. Okay? I will send you some short math review notes which gives these definitions because some places we will use these things. Okay? So that's what closedness means. Boundedness means, again, for our purposes, it doesn't expand to infinity. So this set is bounded, this set is bounded, this set is not bounded. Okay? Because it expands to infinity. Okay? So the only set which is closed and bounded is this set. So this set is a compact set. Roughly, that's, intuitively, that's what you should understand. But I'll send you a note, a math review note, which defines what we mean by boundary, compactness, closeness, interior points, and all that stuff. Okay? But roughly, that's what we mean. So if you have a set of this form, and your functions, numeric representations are continuous, then you are guaranteed for the existence of a Pareto efficient strategy profile. Okay? Before we call it a day, did everybody sign the attendance sheet? Okay. So before we call it a day, so now we have how many animals? Strict dominant strategy solution concept. Dominant strategy solution concept, Pareto efficient strategy profiles, solution concept. What you should ask yourself is, how are these three related? Is there any relation between the set of Pareto efficient strategy profiles and the set of dominant strategy solutions of a game? Okay? Ask yourself, and either try to prove or give a counterexample for the statement where we remove the finiteness. Okay? So is this true for any game? If it's true, try to prove it. If it's false, try to give a counterexample. Okay? That's it. Have fun.